Hey everyone, welcome back. This is the second video in our review of Unit 4. In this video, we're going to be covering questions 7 through 13. So let's go ahead and get started. Let's go ahead and take a look at number 7 now. Number 7 tends to be a tricky one for students to kind of wrap their heads around, but it's kind of a fun one to think about. It tells us that f is continuous over a closed interval and that we have the two endpoints of that, the two endpoints of that interval. So at negative 2, we have a value of 0. So this is at negative 2. And at 2, we have a value of 0. Now this function is continuous over that closed interval. That means we've got to connect these 2 points somehow. But notice it doesn't say that it's differentiable. That's a key factor there. So pay attention to that. Now it also gives us some information here. It says there is no c value for which f prime of c is equal to 0. So we can conclude this. We can say something like this. F prime of x is never equal to 0. Okay? We can conclude as a result of that, therefore, that implies that f has no horizontal tangents. Right? So when f prime is 0, we have a horizontal tangent. Well, because f prime can't equal 0, we have no horizontal tangents. Well, if this function is continuous, we've got to connect these dots somehow, but we can't have f prime being 0 anywhere. So if we just connect the points from negative 2 to 2, we just draw a nice constant line, just at 0, just a straight line, boom. That would be nice, it's continuous. The problem is, then f prime is 0 for all values between negative 2 and 2. So that must imply that the function has to go up, and then it has to come back down. Or it has to go down and then back up. Or any combination, it could go up and down a million times. But it can't stay at 0 forever. In fact, it can't stay at 0 for any moment in time or any interval of time, because then f prime would be 0. So I might have a function that goes up like this. Yeah, that looks good. But then again, f prime is 0. F prime is 0 at that x value. So that can't work. Well, what if we go down like this? Well, then f prime is 0 here. So we're beginning to see that we have a little bit of a problem here with the idea of differentiability. If the function is continuous and f prime is not 0, that means that the function has to look something like this. It has to go up and then down, or down then up, but in a manner where you get no horizontal tangent line. So you might get something that looks like this. That works. That fulfills the requirements of the problem. The function's continuous, and f prime is not 0 anywhere. So you can kind of see that we could have a lot of different functions that fulfill the requirements of the problem, right? Something like that. Maybe we have a cusp or something, right? Maybe we have, I don't know. We could have an infinite set of things. But the bottom line is, since f prime can't be 0, that means the function has to go up and then down somewhere, which means it changes direction. Well, if you think about it, the function can only change direction at critical points. Well, critical points, if you remember, are when f prime equals 0. We can't have any of those. Or at endpoints, well, it can't change direction at endpoints, so that's out of the question. The only other option is when f prime does not exist. And so out of all those options, we would conclude that E is actually the correct answer. It says for some c value between negative 2 and 2, f prime of c does not exist. So E is our correct answer. We'll quickly go through the other ones here. For A, it says that f prime must be greater than 0 for all those values, all those x values. Well, if f prime is greater than 0 for all values, that means the function's always increasing. And it can't always increase because it has to end up at the same height that it started with. So that's out. For B, it says f prime has to be less than 0, which means f is always decreasing. Well, again, that can't happen for the same reason. Option C, it says that for all C values in between -2 and 2, f prime must exist. Well, that can't happen because if f prime existed for all those values, f prime would have to equal 0 somewhere. And it can't happen there. And then for D, this is just a contradiction in terms. It says that f prime exists, but f prime is not continuous. Well, that doesn't make sense at all. F prime has to exist everywhere, but if f prime is not continuous, that means f is not differentiable at that point. If f is not differentiable, then f prime can't exist. So that's just a contradiction. So that leaves E as our only option there. All right, for number 8, we're given f prime of x. Write that down real fast. So f prime of x is equal to sine of x cubed minus x, and that's for the interval 0 is less than or equal to x is less than or equal to 2. And we're looking for the intervals for which f is increasing. So again, the first thing we want to do is make sure we justify what we're looking for before we actually solve the problem. So f is increasing. We would say f is increasing when f prime is positive. Okay? So that's what we're looking for. We're looking for when f prime is positive. And again, that's all found from the chart there. Now this is a calculator-based problem, so what we need to do first is figure out the zeros of f prime. So we want to show this expression, we want to show this work as if we were going to solve it, but we're not actually doing analytical work to solve it. We're going to use our calculator to do the work for us, but we should still write down the equations that we're actually trying to solve. So we're going to set f prime equal to 0. So 0 equals sine of x cubed minus x. And then we're going to go ahead and solve that equation. Well, to solve that with our calculator, it's pretty easy. What we want to do is graph the function, put it in our y-list, graph it, and then find the zeros. And we need to make sure that we're looking at an interval that includes 0 to 2. And that's all we really care about. So we could zoom in as long as we see that whole window there. If we were to graph f prime, it looks something like, starting at 0, it goes down and then up, and then down, and then up, and then back again. And you'll notice that when you go to solve this, we have it at 0. So x equals 0 is when f prime is 0. We have another point. Let's see, we have another point at 1. Okay. And we could easily see that. 1 cubed minus 1 is 0, sine of 0 is 0. But then we have another point at 1.691. And then our last point, if we're looking at this, actually is outside the interval of 0 to 2. The next point is 2.025. So that's outside of the interval, so we don't have to look there. So this is 1. This is 1.691. And then this point is actually beyond 2. So 2 is somewhere here, and the function dies off right here. Okay? So that's the graph of f prime. All right, and since we are looking for when f prime is positive, and we're given the f prime function, we don't have to take the derivative, we just need to look for when it's positive. So that's what the graph looks like. Well, as a result of that, if we're looking at a number line of that graph, because I just think it's easier to look at the number line rather than the graph itself, we have 0, we have 1, we have 1.691, and we have 2, and we have f prime is 0 at those 2 points and 0 at 0, and then at 2, that's an endpoint. Okay, so then we can see, based on that, f prime is going to be negative from 0 to 1 because f prime is below. F prime is positive from 1 to 1.691 and negative from 1.691 to 2 because, again, we're looking at the f prime graph. So f prime is positive when it's above the axis and negative when it's below the axis. So we can conclude as a final answer, f prime is positive over the interval 1 is less than or equal to x less than or equal to 1.691. And then again, our justification is up at the top. F is increasing when f prime is positive. So that's our answer there, which means our answer was B. All right, for number 9 gives us a table. So we're going to go ahead and write down this table so we can get an idea of what we're looking at here. Number 9, it gives us different velocities for certain times. So when time is 0, we have a velocity of 2. When time is 1, we have a velocity of 1. When time is 2, we have a velocity of 0. When time is 3, we have a velocity of negative 3. And when time is 4, we have a velocity of negative 1. Now, it's asking us to graph, and I know it says which of the following could be the graph. It was a multiple choice question at one point, but I deleted the multiple choice options. It says which of the following could be the graph of the position of the particle from 0 to 4. So we're looking for the position of the particle given velocity. So how do we go from velocity to position? Well, that's the antiderivative. The antiderivative of velocity is position. If you remember back, though, the antiderivative of a function is a general function. We have that plus c in there at the end. So we would say an antiderivative of velocity is so-and-so. And so it gives us a little bit more information. It says that at time t equals 0, the particle is at negative 3. So it actually gives us a position at t equals 0. So when t equals 0, the particle is at negative 3. So I'm going to go ahead and use a different color to represent my position graph here. We know when t equals 0, the particle is at negative 3. So we have a point there. And then it tells us certain velocities. Now, granted, it doesn't give us the velocities in between, so we can't come up with a perfect graph, but we can kind of estimate what it's going to look like based on the velocity. Now, remember, the velocity is the derivative of position. In other words, it's the slope of the position graph. So when t equals 0, we're at a position of negative 3, and we have a slope of 2. So maybe it's something like this, a slope of 2. Then when t equals 1, we have a slope of 1. So maybe we have a slope of 1. It's a little bit less than at 0. And then at 2, maybe we have a slope of 0. So maybe it's going to look something like this, right? And then at 3, we have a slope of negative 3. So it's going to dive steeper. It's going to be steeper here than it is here or here because we have a slope of negative 3. And then at 4, we have a slope of negative 1 again. So it kind of shallows out here. So we're kind of connecting the dots and following the path that it's prescribing for us. Now later on, we're going to talk about something called slope fields when we get later into calculus, actually second semester calculus. But we can kind of get an idea that wherever the position is, it has this steepness to it at these different points. So we can roughly come up with a sketch that looks something like this. Now this is not perfect in any way, but we should see, when we're looking at a list of options, I guess you could say, you should see a steeper area, a steeper slope at 0 than at 1, and then it should kind of flatten out at 2, then it should go really negative, it should be decreasing a lot, and then kind of not, still decreasing but not as much. So if you have a graph that looks something along this line, that would be the graph of the position given certain values of the velocity. So that's a look at number 9. For number 10, there's a lot of information here. This is a lot of words. A lot of words on number 10. So let's take a look at what it says. It says that f prime of 5 is negative 3 and f double prime is greater than 0 on the open interval 4 to 6. So we know it's continuous. We know f is continuous. We know it's twice differentiable, which means we can take the derivative and the second derivative, okay, on the open interval. And we know some attributes about this graph, and it gives us some tables to choose from here. So the first thing I want to note is that the function is continuous over the closed interval and differentiable over the open. And so I will recognize that the mean value theorem is going to apply in this problem. That's the first thing I see. Because it's continuous over a closed interval and open over an and differentiable over an open interval, So the mean value theorem applies, which means the average slope between 2 points will be equal to the derivative somewhere in between, and that's going to come in handy for when we check these things. The second thing I notice is that f double prime of x is greater than 0. So as a result of this, we can conclude two things. We can conclude that as a result of that, the f is concave up, right? F is concave up. And we can also conclude that f prime is increasing. So those are two things that we can conclude based on that statement. And then we also know that f prime of 5 is equal to 3. So the slope of the function at x equals 5 is equal to negative 3. So these are some things that we know, and then it gives us some data points for different options. So let me just go ahead and take a look at option A here. It says for x, f of x, we have values of 4, 5, and 6 for our x values, and 8.5, 5.5, and 2 for our f of x values. Now, what I like to do on these types of problems is I like to add an extra column here. I'm going to extend this out. And now I want to look at f prime of x. Now, we don't know the exact derivative at some of these points, but we do know the exact derivative at 5. So when x equals 5, we have a derivative of negative 3. So that's huge, because we can now interpret this statement here in light of this. We're going to apply the mean value theorem and the idea that since f double prime is positive, f prime is going to be increasing. Well, if the derivative is negative 3 here, that means the derivative after 5, after x equals 5, must be greater than negative 3 because f prime is increasing. Since f prime is increasing, the next derivative has to be greater than negative 3. And the derivative before that must be less than negative 3. And so what I'm going to do is I'm going to find the average slope between 4 and 5 here. So the slope between 4 and 5, well, we have a drop of 3 over a run of 1. So our slope, our average slope between x equals 4 and 5 is negative 3. So I'm going to put a little caret here, a little arrow here. So the slope, average slope between those 2 points is negative 3. Now that tells me a lot. By the mean value theorem, since the average slope is negative 3 over this interval, there's a derivative that's equal to negative 3 at some point between 4 and 5. We can apply the same idea after 5. So the slope from 5 to 6, we'll note, is a drop of 3.5 and a run of 1, so that's negative 3.5 here. So what we see here is we see that the derivative is actually not increasing along the way here. The derivative is kind of staying at negative 3. We don't know what's happening in between, but we know that the slope, or the derivative between, the derivative for some x value between 4 and 5 is going to be negative 3. The derivative at 5 is negative 3. Therefore, f prime is not increasing. And in fact, if we look at the derivative for some value between 5 and 6, it is less than the derivative at 5. So we see actually a decrease in the derivative. So A is not a valid option for this question. Now I'm not going to go through each and every one of these. I'll look at two more. Obviously I'm going to look at the correct answer, but I want to give another look at a different one so we can see what's actually happening here. We can say, let's say we take a look at option D. Option D gives us x and f of x values of still 4, 5, and 6 for x. And then we have 9, 5.5, and 1. So we're going to use the same principles here. We're going to find the derivative the best we can. And we know the derivative at 5 is negative 3. The derivative for some value between 4 and 5 is going to be equal to the average slope between 4 and 5. So we have a drop of 3.5 over 1 in between there. And then we have another average slope afterwards, a drop of negative 4.5 over 1. So what we see here is actually kind of a mess. We see that the derivative is increasing and then it's decreasing, which means f prime is not consistently increasing throughout that table. So let's go ahead and take a look at the correct answer. Take a look at the correct answer here. So option E has f of x values of 9, 5.5, and 3. It's E here. And we know that the derivative is negative 3 at 5. The average slope between 4 and 5 is negative 3.5. And the average slope from 5 to 6 is negative 2.5. So since the average slope between 4 and 5 is negative 3.5, that means the derivative is equal to negative 3.5 for some value between 4 and 5. Same logic for the derivative for some value between 5 and 6. And as a result here, we see that the derivative is actually increasing. F prime is increasing, which implies that f double prime is positive, and that's what we wanted. So this option makes all of this hold true, and so our correct answer is E for number 10. Okay, for number 11, we're given f prime. So is that f prime of x is equal to 6 over x plus 1 minus x. And we're looking for which interval f is increasing, or intervals for which f is increasing. So again, let's start off with our justification. F is increasing when f prime is positive. So to determine when f prime is positive, the first thing we have to do is look at the derivative and see when the derivative is equal to 0, when the derivative does not exist, and at endpoints. So we're looking for our critical points because our critical points show possibilities for where the function could change direction. So the first thing we're going to do is we're going to say, I guess we could say f prime of x equals 0. So we'll set that equal to 0. 0 equals 6 over x plus 1 minus x. And this problem is completely doable without a calculator. So we're going to go ahead and solve this by adding x to both sides. So we get x equals 6 over x plus 1. We'll go ahead and cross multiply here. So we end up with x squared plus x equals 6. We just multiplied those two. And then now we have a quadratic, so we're going to move the 6 over and then factor. So the factors are going to be x plus 3 and x minus 2. And so that means we get a solution of negative 3 and 2 for which f prime is equal to 0. So now we're looking for our other critical points. So we're going to be looking for when f prime does not exist. And we can see that pretty easily. F prime does not exist when we divide by 0. So we would say that happens when x equals negative 1. So now we have critical points. We have critical points of x equals negative 3, negative 1, and 2. And so we're going to take a look at what happens on intervals that are around those points. So we're going to draw a number line here. And this function is continuous, or the domain goes off to negative infinity here. So negative 3, negative 1, and 2. And for f prime of x, we have a 0 at x equals negative 3. We have a does not exist at x equals negative 1. And we have a 0 at 2. So it's going to be our job to figure out the signs of the derivative within each of those intervals. So when x is less than negative 3, so I'll plug in like negative 4. So if I find, I'm going to just do some little chicken scratch work up here. If I find f prime of negative 4, if I plug in negative 4 here, I get negative 3 in the denominator. So 6 divided by negative 3 is negative 2. And then minus negative 4. So negative 2 plus 4 is actually 2. So this is going to be positive in that interval. And now I'm going to plug in, let's say, negative 2 here. So f prime of negative 2. If I plug in negative 2, the denominator becomes negative 1. 6 divided by negative 1 is negative 6. Negative 6 minus negative 2 is negative 6 plus 2, which is negative 4. So we get negative in that interval. And now we'll plug in a number in between negative 1 and 2. I think the easiest one is 0. So if I plug in 0 here, I get 6 over 0, which is 6. Sorry, 6 over 1, which is 6, and then minus 0. So we would say f of 0 is just 6. So that's going to be a positive value in that interval. And then we're going to go ahead and plug in a value greater than 2. So I could plug in 3, 4, 5. I'm going to plug in 5 because I know that one works pretty easily. But you can plug in any number greater than 2. If I plug in 5, the denominator is 6. 6 divided by 6 is 1. So we got 1 minus 5 is going to end up being negative 4. So that's a negative value. So we have all the signs of the derivative within each of those intervals. One thing I do want to make sure that we're clear on, that we don't just assume since this one's positive and then negative, it's always going to bounce back and forth and back and forth. It doesn't always happen like that. It just conveniently happened in this case. So you need to make sure that you're checking the signs within each of those intervals. So now that we have this number line, again, the number line is not justification. Our justification came up here. And so our answer is when f prime is positive. So we can conclude that f prime is positive over the interval negative infinity less than x less than negative 3, and negative 1 is less than x is less than 2. Sorry, there should be a negative infinity less than x less than or equal to negative 3, and negative 1 is less than or equal to x is less than or equal to 2. And so we would say that since f prime is positive, f is increasing over those intervals. For number 12, it gives us a lot of information about different functions. It says that f prime and f double prime are all positive for all real numbers of x. And we're to draw a possible graph of f. Now I like this problem because it requires us to understand our chart in a very good way, in a very in-depth way. So the first thing I'm going to do is I'm going to interpret what this all means for the graph of f, because that's my goal. I'm trying to graph the function f. So it says that f of x is positive. So since f of x is positive, that implies, we could say, therefore, f is above the x-axis. Okay, so that's the first thing we know. Since f is positive, f prime is above, or sorry, f is above the x-axis. Then it says that f prime is positive. Since f prime is positive, that implies for f that f is increasing. And then finally it says that f double prime is positive. Okay, f double prime is positive. Therefore, now here's where we got to be careful, because what happens if I were to say graph f prime? Well, we'd be looking at different things, but it says graph f. So I always want to interpret these things in respect to f, because we're trying to graph f. So if f double prime is positive, that tells me that f is concave up. So that's the bit of information that it tells us. So it's our job to graph the function f, or a reasonable function of f, given those attributes. So we know that it must be above the x-axis for all values, it must be increasing for all values, and it must be concave up for all values. So I can think of a pretty quick function that gives me all those attributes, and that would be the exponential function. We can see if I have a horizontal asymptote of y equals 0, we will always be above the x-axis. We can see that the function is always increasing, and we can see that it's always concave up. So this is an example of a graph where all three of those attributes are true, And one good example is y equals 2 to the x, or y equals e to the x. For number 13, we are given the graph of g double prime. So we know that g double prime, I'm going to write this down, is given. Okay, and then it's asking for us to find the points of inflection for the graph of g. And so this is where understanding the chart and where things change is important. So we know that g has a point of inflection where concavity changes. So we go from concave down to concave, let me use my hands here. We go from concave down to concave up, we have a point of inflection. Or we go from concave up to concave down, we have a point of inflection at that change. So what does that mean though when we're given g double prime? Well, if we are changing concavity, that means if g is changing from concave up to concave down, that would imply that g double prime is changing from positive to negative, because concavity of a function is determined by its second derivative, or the sign of its second derivative. So we could conclude that if we're looking for the points of inflection of g, we're looking for when g double prime changes signs. So we'll justify it like this. G has a point of inflection when g double prime changes signs. Okay, so that's our justification here. And since we're given the graph of g double prime, we're just looking for when it changes signs. In other words, we're looking for when it changes from being above the x-axis to below the x-axis, or vice versa. So if we look at this graph, we can see at point A that g double prime is changing from being below to above, which means it's changing signs from negative to positive. Therefore, we'd say when x equals a, and I'll add a little bit of justification here. Since g double prime changes signs from negative to positive. Okay. Now, it doesn't matter which way it changes signs as long as it changes signs, but it's always a good idea to be as detailed as possible. And then we also have another one when x equals f. When x equals f, since g double prime changes signs from positive to negative. Okay, and so our final answers are when x equals a and f. Now, a couple important things to note about this particular problem, because I'll see students try and give me different answers with different justifications. I'll have students say when x equals b, x equals c, and x equals e, because g double prime is changing direction. And that's not the case. That would be true if this was a graph of g prime, then we would be looking for when g prime changes direction in order to give us a point of inflection for g. And to kind of justify that a little bit, you would see since g prime is changing direction, that means it's going from increasing to decreasing, or vice versa. That would imply that the second derivative is changing from positive to negative, which would imply that g is changing from concave up to concave down, point of inflection. So you have to be really careful about what graph is given. So I'm always looking for what is given and then asking myself, how do I interpret that in the light of the graph that was given? So since I was given g double prime, I want to make sure my justification all revolves around the second derivative, not something else.